Last unit on measurement, this is volume and capacity. I wonder if you know the difference between those two. Well, we're going to find out. A volume is the amount of space contained within a three-dimensional object. So we are going into 3D land here. Okay, so it's the amount of space contained within an object, and I think you probably already know we use cubes here. How many cubes can fit in any particular shape? And this is a hard one. This is not so hard to work out the number of cubes in there, perhaps. And the cubes could be anything. Could be 1 centimetre by 1 centimetre by 1 centimetre, or metre by metre by metre for bigger objects. So that's the idea. Look around the screen here, and some of these you will have seen before. Anyway, we're going to investigate all of these solids and some more as well, and see if we can describe the amount of space inside. How many cubes will fit in there? And so we get the unit 1 centimetre cubed. Centimetre by centimetre by centimetre is a cubic centimetre. All right, get the idea. Capacity is how much fluid will fit in there. And so that's a similar idea, except it's a different unit, isn't it? We have litres and millilitres. So leave that for later on. Let's come down and look at the basic units now and how to move between them. So here are our units, volume units. 1 centimetre cubed is 1,000 millimetre cubes. Hang on. There's only 10 millimetres in a centimetre. How come it got to be 1,000? Well, let's check it out now. Let's say we have a cube here, which is a centimetre by a centimetre by a centimetre. Okay, but each centimetre is 10 millimetres, isn't it? 10 millimetres by 10 by 10. So 1 cubic centimetre actually contains 10 by 10 by 10, or 10 cubic millimetres, or 1,000. That's how you work it out, unless you just memorise it. You get the idea there. What about 1 metre cubed? How come it's 1,000,000 centimetre cubes? There's only 100 centimetres in a metre, but hang on, it's a cube, mate. So let's have a look here. So if it's a cubic metre, a bit rough this one, that's a metre, but that's 100 centimetres. This is a metre, that's another 100 centimetres. This is a metre, making a cubic metre, that's another 100 centimetres. So 1 metre cubed is 100 cubed, 100 by 100 by 100, length by breadth by depth. We're going to look at that in a minute. Centimetre cubes, which is 1,000,000, or 10 to the 6 centimetre cubes. So when you're looking at cubic things, your milli and your centi prefixes have to be adjusted. You've got to cube them, because each side then has got that, if you like, factor. Okay, so conversion diagram, this time again from Hayes and Harris Publications, 11 apps there. If it's a big one going to small ones, you're going to get more your times. Okay, same idea before. If you're coming back from smalls to bigs, you're going to divide. You have less of them. Same conversion method. Come down, I want you to have a go at a few here. Oops, I don't want you to see the answers there just for the minute. Go down there. Okay, so there we are. I'd like you to have a go and see if you can do these conversions. The last one's a little bit different. Okay, you're trying to find how many 5 centimetre cubes in sinkers you can get out of this, so you're going to have to change that to centimetre cubes as well. All right, see what you think. You might have talked to your teacher about the last one. Pause it, have a go. I'm going to show you the answers now. Here we are, there are the answers. All right, did you get 47,400 sinkers, I wonder? All right, let's move on to actual volume calculation rather than just conversion of units. So here we are. The first lot here are what we call uniform solids. That means they've got the same. If you cut through there and look at the ends, it's always the same as that end there. And this one, if you cut through parallel to there, you would always get a triangle shape looking on the end. And if you cut through here, you would always get the same shape on the end, which would be a circle. So they're called solids of uniform cross-sectional area, or cross-section. When you cut across them, section across them, they're uniform all the way. They don't taper. This is an example of one that is not uniform cross-section. You get smaller and smaller circles as you go down that cone. We're not talking about that. We're talking about ones that when you cut through you get the same shape on the end. Let's have a look at how we might calculate the volume. Here I've done an easy one for you. Okay, so let's take this area here, and of course you know area consists of squares, not cubes, it's just a flat surface. So how many squares can I get across that face? Okay, how many squares? So you already know this one. The area of this end, so area is the number of squares you can make, and here it is, what? Length by breadth. We explained that in the last presentation. That's the number of squares. Now how do you make a cube? Well, let's slice it like a piece of cheese, 1 centimetre back. Okay, 1 centimetre back there. And if I did that, can you see what's going to come out of that? It's going to form a whole lot of cubes. A whole lot of little cubes are going to drop out off the end of that. And how many cubes will we have for each slice? Well, hang on. Each of these squares are going to form a cube. So 1 centimetre slice backwards is going to produce length times breadth, lots of cubes. Now, if we keep going, and we do another one, slice through there, get another layer of cubes coming off, and do it again, etc. How many slices can we do? That depends on D, the depth in centimetres, or in metres, whatever unit. So if we keep doing it, we'll have D slices would give D lots of length times breadth. Oh, I think we've just found the formula. The volume is length times breadth times depth. That's the total number of cubes that we'll be able to slice off of that. Do you get the idea now? Okay, I wonder if you ever thought about how to find the volume, why the volume is length by breadth by depth. Oh, hopefully that helps you. Let's go down now and have a look at these others that we said. And there's what we've got. The volume of a body with uniform cross-section is the number of squares you can get on the end. So A is the number of squares, the area of the end, times the number of slices. Or V is the area of cross-section times the length of the body. We did it for this one. The area of that was L times B. I will better call it breadth times depth now. So the area of the end is breadth times depth, and then you times it by the length. What's the area of this end? It's a half the base times the height. That's the number of squares. So work that out, and then times by the number of slices. It's easy to remember if you know how it works. Get up close and personal with maths. It's a lot easier. So what's the area of this end? How many squares across there can we get? It's pi r squared squares. And then we'll keep slicing, won't we? And each slice will have squares drop off. Now, sometimes you won't get a perfect square, but all the little pieces added up will effectively give a whole number of squares, or a partial number of squares anyway in your answer. But the notion is still the same. Area of the end is the number of squares equivalent that would fit across there, and then when you times by L, you convert them to cubes, don't you? Alright, so there's our first formula. Please remember it. If the body has a uniform cross-section, you get the area of the cross-section and times the length. Okay, let's go down and have a look and see about the others though. What about if you've got something like this? There's pentagonal here. Base is a pentagon. And the thing is a tapering solid. It tapers up. Now all of these are the same shape but different sizes. Same shape. And so they are connected to each other by a process called enlargement in maths. One is the enlargement of the other. Same shape but different sizes. Well, this is a problem. You can't use the same idea now because you haven't got length, lots of, if we call this the height or the length of the body. You can't say it's L lots of the same area because look at them, they're getting smaller. So what are we going to do? Let's have a look at some examples here. There are some examples, and here we have the rule. Now, this course, because you don't do something called calculus in this course, I can't actually show you where this formula came from. It's higher mathematics than what you're doing in this course. But here are some bodies. Pyramid, triangular, because that's a square-based pyramid, triangular pyramid, and here's a cone. And each of them are tapering. Can you see they're tapering upwards? So they're getting smaller and smaller until they reach a peak or an apex. The formula here is a third the area of the base. This third allows for the tapering. Okay, times the height. So here, example might be that we write down a third A times H. So this one here, the volume is a third, what do we kind of call the base? Length by length. A third L squared times H. This one here, a third the area of the base, which is a half base times, let's call that the altitude there. Base times altitude, and then the height. So we've got two sorts of heights here. The height of the figure and the height or the altitude of the triangle in the base there. And what's this one? The volume of this one is a third the area of the base, which is pi r squared, it's a circle, times h. So here's your rule. And I guess the idea, have a look at this one, I'll just show you an idea here. If I did the whole cylinder, there's a cone in the centre there, like that. The area of the whole cylinder, the volume of the whole cylinder is pi r squared, that's uniform cross-section, times h. What we're saying here is when they taper, this tapering solid in the middle occupies a one-third of the complete object. Here it's a cylinder. Okay, so that's the idea, and we could draw it for each of them. Complete the whole cone here, for example. What would be, hang on, let's get this right here. It would be like this, and that whole triangular prism, for example, would have the volume of half base times altitude and then times the height. But it doesn't fill that whole continuous triangular prism, and so it's a third of this is occupied. That's the idea. Anyway, a little bit of maths there. Let's go on now and try to use it and do some calculations. Well, first of all, we better do one more. The sphere, again, you need calculus to prove this, so you're going to have to just learn off in monkey fashion. 4/3 pi r cubed is the volume of a sphere. Okay, so we're trying to fit cubes in there. Trying to fit cubes in there. All right. So 4/3 pi r cubed. So there's a few things to remember here. So you might make notes. Note those down. And let's have a look at using them here. Well, example 27 isn't too bad. Calculate to 1 decimal place the volume of the uniform solid. What that means is when you cut across it, now just be careful which way you cut. Well, there's the end, the area. If we cut through here each time, then they would all be that same shape, wouldn't they? Notice you can't cut this way. Okay, so you have to cut through from the end along the body so that it is uniform when sectioned or cross-sectioned. Sectioning means cutting across the body. So what is it? It's the area of the cross-section times their length. So it's 11.7 centimetres squared times 5.9 is, to one decimal place, approximately 69.8. Because we've rounded off, we should put this approximately sign, or that sign, approximately, and one decimal place in brackets would be good. All right, are you ready to try to pick out the ones and use the right formula? Here we are. Question 4, quite a few parts here. Decimal place, to 2 decimal place, find the volume. So if they're all of uniform cross-section. So if you know the area, it's simply times the height, because every time you cut through here, a load of cubes come out. All these centimetre squares become cubes. Remember that one? Volume is the area of the cross-section times the height or length of the body, whatever you want to say. All right, pause the presentation, have a go, maybe at every other part. We'll just bring up the other parts here. Okay, and then I'm going to ask you to mark your work. So I'm going to show you the answers now. Come down, have a look. Here are the answers. Okay, so mark your work. We're going to move on to non-uniform solids now, as you might have gathered. And here's the next set. So here is one that's tapered. So if this is a tapered solid, it tapers to a point, so it's a third the area of the base times the height. And the area of the base, they tell you, is a third the area of the base times the height, this time in metres, just make sure of the units here. And the volume of the sphere has got its own formula, 4/3 pi r cubed. Make sure you use the radius. See here, that's the diameter of the sphere. The formula involves the radius. Be careful there. And again, approximately signs in here because you've rounded off, and we're using 2 decimal places. Most often we use 3 significant figures. We're just revising that. This would be 310 centimetre cubed to 3 significant figures. All right, want to have a go? Come down and have a look here. Got some for you. Question 5. Try most of the parts there, practicing the formula. Okay, pause the presentation and then I'm going to show you the answers. All right, so here are the answers now to question 5. All right, hope you're going well. It's a matter of just identifying the type of problem that you've got. Is it a uniform cross-section or not? And then away you go. All right, let's have a look at some other applications here and see what we can come up with, 6, 7 and 8. Now they ask us about a percentage increase here in this problem, so I just want to revise that. A percentage increase, like this little fellow's saying here, is you find how much the value is increased and you always divide by original and times by 100. Okay, so please remember that definition. But percentage increase always means taking the increase as a percentage of the original. Okay, have a go at 6, 7 and 8. Watch out for this one because we've got the volume of that amount of concrete there. The pipe in here is hollow. We might have to take this hint here. Okay, watch the units as well. Make sure it's always everything's in metres or centimetres. It's consistent. Have a go. I'll show you the other questions and I'll show you the answers. Okay. I don't think I can get them all on. So there's 9, 10, 11. You might just try a few of these. Pause presentation, have a go. And now number 12. Okay. All right, so let's have a look at the answers. Oops, too far there. There's just 6A. So little bit of a diagram there to help you. Check your units and make sure it's always consistent. Okay, let's move on to some more variety of problems here. Okay, what about this one here? This is a little bit harder. Find to one decimal place the value of R. Yes, that's right, R. You don't know the radius. So the height of the cylinder is given and you want to know how wide to make it so it contains 54.03 centimetre cubes. So first of all you write down the formula. This body is a uniform cross section. If you section it through there, you always get that end shape. So the formula is area cross section times length. Pi r squared times length is 54.03. Now, if r squared is being multiplied by these two things, then to get r squared back again, you'll divide by them. Okay, dividing both sides by those two numbers. And then you can do it on the calculator. The square root, you need to take the square root of that. And you should explain that r is greater than 0. Because there are two answers to r squared equals that. It's a positive number or a negative number. Remember, the square root of 4 is either 2 or neg 2. Because neg 2 times neg 2 is also 4. Alright, or you could use the calculator. So you'll use the calculator just to do the multiplication. Or there is a function on the Casio to solve equations. So if you go to Equa on the menu and then go F3, which is to solve, you can put that whole equation in. Instead of r squared you'll put in x. And here's the syntax. And then you start with a guess of the solution and a bound for the solution. Okay. You've got to select the guess and then go to solve it and it'll give you an answer. So have a look at that, play with that. I'm not a great fan of solver on the Casio. I would like you to do it back up here by doing this simple rearrangement. I think you should be able to do that. Anyway, there's an option for you. Let's have a look at some problems where you do have to rearrange them. In other words, you're given the volume and some of the dimensions and you've got to go backwards and find the rest. Okay, let's just look at that first one. Uniform rectangular prism, area cross section times the height. Now we know the volume here is 40, area of cross section will be 5 by 3 by the height. I don't think it's too much to ask you to divide both sides by that and find the height. Okay, have a go at each of those. They're all ones where you know the volume and you're working back to find some dimension that's missing. Alright, let's keep going. We've got some interesting stuff coming up still. There are the answers to those questions above. Alright, let's go on and have a look at capacity. Now, this is very similar. You're talking about a 3D body, like this one, and it's got a volume, a centimetre by a centimetre by a centimetre. But what we say with its capacity is we're saying how much fluid can it hold. And the only difference there is you're describing the space inside in different units of measurement. Different units for volume. So technically, when you say the volume is the amount of space inside, you're going to talk about 1 centimetre cubed. If you talk about the volume of fluid, we measure that in litres and millilitres. So 1 centimetre cubed contains 1 millilitre. So 1 millilitre will fit exactly in 1 centimetre cube. 1 litre has to fit in 10 centimetres by 10 centimetres by 10 centimetres. So that's our going between the units for volume and the units for capacity. How much fluid? Okay. So there are, of course, 1,000 millilitres in a litre. Okay, I think you probably know that because milli means 1,000th. Okay, same nice consistent metric system there for our volumes as well. Remember the prefixes. Okay, so here are the crucial things. Let's bring it all up now. The conversion as well. We say 1 millilitre is equivalent to. That sign does not mean equals, it means equivalent to. Okay, equivalent to. Okay, 1,000 litres is 1 kilolitre. It's equivalent to a metre cubed. Okay, equivalent to. Because they are different units. We're just saying if you're converting them, and here we are down here, then the conversions look like this. 1,000 millilitres is a litre. 1,000 litres is 1 kilolitre. Same thing again. Going from bigs to smalls, you're going to have more, you're going to times. Then litres to millilitres, that's 1,000th of a litre, you're going to times again. Coming back, you're going from smalls to large, you're going to have less large, you'll divide. Okay. Same idea. What's the prefixes? So they're a guide to what you're going to multiply or divide by. Let's have a look at some problems now. Or maybe just bring all these up. Let's convert 4.2 litres to millilitres. Litres are bigger than millilitres. So you're going to have more little ones. How many? Milli is 1,000. So you'll times because you want more and by 1,000. What about 36,800 litres to kilolitres? Kilolitres are bigs. You're going to get less of them than what you've got of litres. And therefore you're going to divide, and how many litres in a kilolitre? Kilo means 1,000, so every 1,000 you want to divide by 1,000. Okay, I'm going to leave you with these two problems, 14 and 15. Pause the presentation and have a go, and I'll show you the answers. Alright, there they are. Very good. Right, what I'd like to do now is just an additional little thing here about volume and capacity. Just a little table you might copy down. 1 centimetre cubed is equivalent to, not equal to, equivalent to, 1 centimetre cubed holds 1 millilitre. 1,000 centimetre cubes holds 1 litre. 1 metre cubed holds 1 kilolitre. And 1 metre cubed is therefore 1,000 litres. Alright. Try to remember those, make some notes. Alright, let's keep going now and have a look at some conversions. Okay, 16 and 17. So we're going backwards from your capacity in litres to your volume, the amount of space inside. So 9.6 litres, a litre occupies 1,000 centimetre cubes, so multiplying by 1,000. 3,240 litres to metres cubed, you're going to therefore say here where every 1,000 metre cubes makes a or fills a metre cube. So you want to know how many thousands there are in there. Okay. So just watch that using those conversions. Have a go. I'll show you the answers. That's just remembering there what litres occupy in terms of metre cubes and so on. Okay. Let's have a look at the answers. And there they are. Alright, so it's pretty much the same stuff as we've been doing, just in a different sort of context, now in a volume and capacity context. Let's have a look at a practical problem here. How many kilolitres of water would a 3 metre by 2.4 by 1.8 metre tank hold when full? This is very important when we're trying to conserve water. It's a square tank, so you want to convert that to metres cubed. There it is. And now 12.96 metres cubed, do you remember? 1 metre cubed is equivalent to 1 kilolitre. Okay, I should have a small k there, really. The prefixes are really a small k. So here 1 kilolitre. Okay, so that gives you an idea. And people are building tanks, you know, you can't rely on the water supply always, so there's some different shaped tanks. I'll just put this up a little bit. There's some different shaped tanks for your house. and you find the volume. Remember, area of cross-section times the height. Just remember that's the diameter. You might need the radius for the area there. Okay, have a go at those few. And pause presentation, I'll show you the answers now. Okay, so there are the answers. All right, let's look at some practical problems. These are important, aren't they? If you're looking at being on the land or supplying water for a family. Oh, here we are, 17.3 millimetres of rain falls on a flat rectangular roof shed, length 10 and width 6.5. All the water goes into a cylindrical tank of base diameter 4. How many millimetres does the water level in the tank rise? Okay, so first of all, it's in millimetres, so let's convert this to metres because everything else is in metres. So this is 0.0173 metres. Millimetres, smalls into bigs, we're going to divide, and there's 1,000 millimetres in a metre. So that is, if you like, the depth on the wall on the roof. So let's have a look here. Let's draw a picture. It's 10 metres by 6.5, and we've now said the depth is very small in metres. This is what we've got now, isn't it, when we're collecting the rain. And that depth is 0.0173 metres. So the volume is the area of the roof, which is 10 by 6.5 square metres times the depth. That's how many metre cubes we've got. So now that's going to go into this tank. So the area of the base of the tank is pi r squared, so radius is that, so it's pi by 2 square metres. Okay, so that's the area. Now, we don't know how tall, how much it's going to fill up, that H there, so let's work the volume out. The volume would be the area base times the height. So it's that 12.56 times 8 square metres. And that has got to contain what we've just found, the volume from the roof. So 12.566 times the height is that. If we divide by 12.566, we will have, everything's in metres, approximately 0.0895 millimetres. And metres, sorry. And so if you want to change that to millimetres of how much height rise here you're getting in your tank, then you will multiply by 1,000. Because this is bigs going to smalls, so you multiply, and millimetres, 1,000th of a metre, so it's 89.5 millimetres. That's useful if you're on the land, and particularly know whether your tank can hold that and so on. Okay, let's have a look at some practical problems here. I want you to pause it, have a go at those. I'll show you the rest now. 24. And might try to do all of them, might not have time, so I'll show you the answers. Okay, have a look at those answers. We've just got one little bit of use of volume left, and I think you're going to find this interesting. Okay, so come on down, and building regulations. You might know, you might go to a nightclub or something like that, or a restaurant. They say, sorry mate, we're full, because there are regulations on how many people you can fit in a venue. And what are those rules? Well, there's an average area allowed per person in a nightclub or in a restaurant. And you should work that out. So you've got to work out your floor area available and divide by the number of people. And that number has to be a certain value. Now this varies around countries and so on. And they've also got to have enough airspace. So this is another number that must be correct. The average volume per person. The volume of the room, breathing space, divided by number of people. And let's say you've got to have 1 square metre. Must be greater than 1 square metre to move in. Let's say this has got to be greater than 1 metre cubed of breathing space. There are some rules like that. I don't know the current figures for this. This is how they work out the capacity of, or number of people that you're allowed in a venue. Okay, let's go down and have a look at an example. Consider our classroom with dimensions shown, 7 metres by 6 metres and 3.5 metres high. They usually aren't that high. So what's the average area here? The area of the base is 42 square metres, there it is, and let's say you've got 29 students, they've put, plus the teacher, so it's 30 people, you're getting 1.4 square metres of floor space each. Okay, that's probably good. What is the volume? The volume is by length by breadth by depth. Uniform cross-section, divide by 30, we're getting 4.9 metre cubes of air per person. Now we could check the building regulations and see whether that is adequate. Get the idea? So this is exciting. You can actually understand where the building regulations come from and check venues out. So I want you to do the same sort of calculation for these three and calculate the airspace and the area of floor space that on the average that those people will have. Okay, available to them. Okay, pause the presentation and let's have a look at the answers. And there they are. All right, now I think this has been a powerful presentation, something is very useful for you in so many different ways. So I hope you've enjoyed it. Go back over it, think about what you're doing, because it's really useful stuff. All right, that's the end of measurement. I hope to catch you in a later presentation. Cheers for now.